Hello, I welcome you all in this presentation related with the subject fundamentals of the manufacturing processes, and we are talking about the manufacturing processes which can be used to improve the performance and properties of the components being manufactured. So, we know that the metal in pure form, whether it is like iron or aluminum or magnesium, any metallic system, if we take in pure form, it offers low strength, low hardness, high ductility. So, because of the limited load carrying capacity of the metals in pure form, they becomes of the limited use for the engineering applications, because what we want that the not just the strength and hardness are good, but also it has combination of the good ductility and toughness. So, in order to improve the load carrying capacity of the metals which are being used for manufacturing different engineering components, it is also important that they have good strength and ductility and good toughness. So, irrespective of the kind of the metals, the various approaches are used for strengthening the metals. So, strengthening of the metals is realized through the various approaches. Some of them are like this, wherein solid solution strengthening, wherein the elements in form of the solute are dissolved in the pure metal in order to increase the strength. This is called solid solution strengthening, wherein the two types of the solutions are generally formed. One is the substitutional solid solution, and another is interstitial solid solution. So, those elements which form the interstitial solid solution, they result in much higher increase in strength and hardness as compared to those which result in the increase in somewhat lesser increase in strength and hardness takes place. So, like nickel copper system is one where substitutional solid solution is strengthening happens, and iron carbon system is where interstitial solid solution strengthening is realized. Another is the grain refinement, wherein the grain size of the constituents or the phases which are present in metallic system are refined. So, like initially if the grains are coarse, then it will have the poorer mechanical properties in terms of the strength, ductility, toughness. So, if we refine the grain structure of the metal, means the phases present are made of the finer size using variety of approaches like heterogeneous nucleation in the casting, or heat treatment, normalizing heat treatment for refining the grains. Then variety of approaches are used for refining the grain structure, and here the yield strength is found inversely proportional to the grain diameter, average grain diameter. So, this is actually related with, this is actually corresponding to the Hall patch relationship or equation, where in the decrease in the average grain size results in the increase in strength of the yield strength and the hardness of the material. And this approach does not result much in much decrease in the ductility and toughness when the grain refinement is used to strengthen the metal. Another is the dispersion hardening. Dispersion hardening is used in case when the soft metal matrix is reinforced with the hard constituents which provide the support to the soft metal matrix. So, the aluminum matrix is fitted with the high hardness silicon carbide or boron carbide. So, such kind of hard particles are reinforced, carbide tools are one of the examples where in cobalt matrix most of the carbide particles of the tungsten or titanium or tantalum are fitted in the matrix. So, this proportion in case of the carbide tools may be like 3 to 12% of the cobalt and remaining used in tungsten carbide or tantalum carbide or titanium carbide. So, in this case every constituent retains its identity and the properties, while the good bonding helps to achieve those properties. Good bonding of the matrix with the reinforcing agent helps to achieve those properties which otherwise cannot be achieved individually by each of the constituents. So, these are basically the typical composite materials. Then we have strain hardening. In case of the strain hardening, this is realized through the plastic deformation of the material. So, plastic deformation using the external forces helps to generate larger number of the dislocations in the material, which if it is having the lesser number of the dislocations, then the movement of the dislocations will be easier and yield strength will be lower. At lower stresses it will be deforming easily. So, generation of the larger number of the dislocations in the matrix results in the increase in strength, and this is called work hardening or strain hardening. Both terms are commonly used, but whenever a strain hardening or work hardening is used, although it increases its strength, it increases hardness, but most of the time at the cost of the ductility and toughness. So, this is not considered to be good in that way. Also, the ductile to brittle transition temperature DBTT is increased when the cold working the plastic deformation for hardening, strain hardening or work hardening is applied. The ductile to brittle transition temperature is the temperature at which there is a sharp drop in the toughness of the material, and which becomes which tends to behave at below which it tends to behave in more like a brittle material. So, work hardening or strain hardening is the another approach. So, these are the mechanisms which use the different approaches like alloying or the refinement or reinforcing of the hard particles or plastic deformation. Now, the two approaches about which we will be talking, and they are related with the heat treatment, is about the transformation hardening. This is typically used for the heat treatment of the steels, where one phase like austenite, which is stable, which is unstable at the room temperature conditions. So, using the different cooling rates, efforts are made to have the different kind of the phases. So, we get the different properties. It may lead to have like ferrite, perlite. It may lead to the ferrite, benite, or martensite, or the benite only. So, the variety of the constituents phases in the different proportions are possible by controlling the cooling rates during the heat treatment. So, one phase is transformed into the different phases in order to realize the different set of the properties. So, this is the approach, one of the approaches of the heat treatment, where one phase is transformed into the different phases in order to regulate the properties as per the requirement, and accordingly the different types of the heat treatments have been developed. And then apart from the transformation hardening, there is one more type of the hardening strengthening process, which is called precipitation hardening. Precipitation hardening is used for certain kind of the systems which show the increase in solubility or to the alloying element with the increase of the temperature. So, like aluminum, copper, titanium is kind of the systems which show and the nickel systems which show, magnesium is also there, which shows the tendency for the precipitation hardening. So, this also involves the heating followed by quenching and then again aging. So, last two strengthening mechanisms like the transformation hardening and the precipitation hardening are the heat treatment processes where which involve like the heating, then soaking, then cooling, or you can say the controlled cooling is realized. cooling, and so this kind of the combination results in the heat treatment, and depending upon the way by which we cool under the different conditions or reheat it under the different conditions, that leads to the transformation hardening or the precipitation hardening. So in this presentation now we will focus on the basics related with the transformation hardening heat treatment, transformation hardening heat treatment. This is mainly for the steels or heat treatment of the steels. So certain things we need to keep in mind when we talk of the steel heat treatment of the steels. Basically heat treatment is carried out in order to change the microstructure of the constituents, so that the kind of phases that will be offering the desired combination of the properties which are produced through the controlled heating, soaking and then cooling. So change in the structure is the, as per the requirement, is in the target for the transformation hardening. So now we will see the what kind of the phases it has and what kind of properties they offer, and for which kind of the systems it is applicable. So if we see the steel is an alloy of the iron and carbon, which forms the interstitial solid solution, but iron in its pure form, when it is cooled from the molten state to the room temperature gradually, so as a function of the time, kind of things that we get in becomes like this. This is the constant temperature, above this it is liquid, and this is where it will be solidifying. So this is in the solid state, so solidification, and then it remains. So solidification occurs say at a constant temperature, then again one transformation takes place, then another transformation takes place, then another transformation takes place, like this. So here we know that we have the alpha or BCC crystal structure at a room temperature. So say this is room temperature, and here it is 1800 degree centigrade as a function of time, and here below this it is the magnetic at room temperature, and this is the temperature in this band it is alpha having the BCC as well, but it is non-magnetic. Above this it forms the gamma. This is normally 910 degree centigrade, then we have the gamma. So this gamma is formed up to this temperature with where it is 1395 degree centigrade. Above this we have delta. So this is the delta, again it is of the BCC crystal structure, and this is of the FCC crystal structure. This is also non-magnetic. So if we see on cooling from the liquid state, it forms first delta, then gamma, and then alpha. So which will be having like first BCC, then FCC, and then again BCC. So there is a continuous change in structure of the iron. Because of this change in structure only, it is called allotropic metal, where in change in temperature results in the change in the phases which will be formed. So pure iron, like normally the commercially the pure iron is mostly used in form of the wrought iron, which has a carbon about the 0.06%, whereas its a strength, maximum strength that it offers is 48,000 psi, while the elongation which it offers is in the range of like 18 to 25%. This is the ductility or the elongation, percentage elongation which iron offers, wrought iron offers. So now if we see the various other phases which are present in the iron, these phases are there, this is the wrought iron is one, and then in steels we have the variety of phases which may be in form of like alpha or also termed as ferrite. This maximum at room temperature, it can have like 0.08% of the carbon, but it offers the very high ductility. Its ductility is it's about 40%. So let's take first the strength. Strength is 40,000 psi, and the ductility is around 40%. Hardness is low. Hardness is either RC0 or RB. Rockwell Brinell hardness is 90 or 95. This is the range. This is for ferrite, and then we talk of if another phase like the gamma, or it is called austenite. In austenite, the maximum solubility for carbon is about the 2%, but it offers the hardness RC40 and the ductility 10%, and the strength is very high, 150,000 psi. As compared to this, the perlite, which is a mixture of perlite, which is mixture of the ferrite plus cementite, ferrite plus Fe3C. So Fe3C offers the hardness of the RB 95 or much higher in case of the means the even higher hardness of RC20, and the strength is 120,000 psi. So from here we can have some idea about the strength as well as ductility. The perlite strength and ductility is 1000 psi, austenite is having 150 psi, while the ferrite is having the low strength but higher ductility. In addition to this, there is one more phase which is extremely common in iron in these steels, that is the cementite. It has got very low strength, like just 5000 psi, and that it's extremely nil, almost nil ductility. So no ductility, very hard and very brittle. So strength wise it's very poor, and it has the crystal structure of the orthorhombic crystal structure. So if you see normally if we want if you have the austenite at a high temperature, at room temperature, it gets destabilized into the different phases. So the cooling rates for the austenite is controlled in such a way that we get the phases of our requirement. So since the different phases like alpha or perlite or Fe3C or perlite Fe3C and the gamma, all these phases have the different properties, different crystal structures. So efforts are made in such a way that at room temperature we have the desired set of the phases in steel, so that required properties can be achieved. So since the transformation hardening is applicable, mainly applicable for the steels, but it can also be there in titanium and the copper based systems. If we see the steels, there are two broad categories. Where in like the carbon steel, where primarily the carbon concentration is controlled, and then alloy steels, where in like for hardening, strengthening, increasing the hardenability, some alloying elements are added like vanadium, titanium, chromium, molybdenum, etc. So these elements have the good affinity with the carbon, and carbon affinity even is greater than that of the iron towards the carbon. So because of the greater affinity of these elements with the carbon as compared to the iron, they easily form their carbides like TiCVC, chromium carbide, and molybdenum carbide. So when these actually carbides are very stable, they do not decompose into the elements like V plus C or MO plus C. So they remain stable, they need longer time to get destabilized. So because of this only, what we see that when we use plain carbon steel, the kind of heat treatment conditions required for achieving the desired properties are found to be different than what is to be used for the alloy steels, because it has the different phases which do not easily decompose, destabilize, and this resists the formation of the homogeneous austenite, which is prerequisite for the heat treatment of the steel. So, so it is important to consider that which kind of the steel is being heat treated. For this for the heat treatment purpose, there are three basic diagrams which need to be considered for applying the principles of the heat treatment. So, these three diagrams are like iron carbon diagram, and then triple T diagram, time temperature transformation diagram, and continuous cooling transformation CCT continuous cooling transformation diagram. We will talk little bit about these three diagrams, because these will be helping us to see how to heat, means heating aspects regarding the maximum temperature up to which heating needs to be done, and these two diagrams will give us idea about what kind of the cooling conditions we should use, cooling rates we should use, so that we get the desired, the structures, desired phases in the steel, so that we can have the desired combination of the properties in the steels after the heat treatment. So, we will talk about the iron carbon diagram first. It is like this, wherein this is the zone of the interest for us. It is 910 degrees centigrade, it is 730 degrees centigrade, this is corresponding to 0.8%, and this is very less, it is 0.025%, and here it goes in like this, although this is not for of interest for the steels, but this occurs at about 2%. So, in y axis we have the carbon concentration in the weight percentage, and in x axis we have carbon concentration, and y axis it is the temperature in degree centigrade, and this is the zone for at 1395 for our delta for phase formation starts. So, in as a result, it results in the presence of one loop, which is called this is called gamma loop, and this is the region wherein austenite will be stable. Although this point is called eutectoid point, which occurs for this combination of the temperature like 0.8% of the carbon and 730 degree centigrade, and these lines, this line is called lower critical temperature line, and this is both these are the upper critical temperature lines, upper critical temperature lines. And the region between the lower critical temperature and upper critical temperature lines is called intercritical temperature zone or the region. So, all this region is the intercritical temperature zone. Okay. So, for the heat treatment purpose, depending upon the carbon content, because basically we know that the steel, there are three types of the steels like low carbon steel, medium carbon steel, and high carbon steels. So, this has less than 0.25, this has 0.25 to 0.5 and greater than 0.5. So, if we see this one as per the carbon content, there are a few more details, like this is the gamma loop, this is the gamma plus alpha region, this is alpha plus perlite region, this is 100% perlite region. Perlite is basically the alpha plus Fe3C alternate layer mixture, and here we have Fe3C plus perlite region. So, in nutshell, this is the band below 730 degree centigrade, where basically we have ferrite and the perlite, maybe individually as a proeutectoid phase or a mixture of the ferrite and cementite, which is basically perlite. So what happens when so since for the heat treatment purpose we need to heat the steel to the austenitic temperature range for most of the steel. Depending upon the purpose we can heat it to the temperature in the anticritical zone or even little bit below this lower critical temperature. About that we will talk later, that how to choose the temperature up to which it is to be heated. So, say what happens when the steel of say 0.2% carbon steel, say low carbon steel, when it is heated. So, the steel, this steel at room temperature is having mainly alpha and perlite. Alpha is say 80% and the perlite is just 20%. So, when we heat, during the heating on reaching to the 730 degrees centigrade, the perlite will get transformed into the austenite, and if we continue the heating, the remaining ferrite will be converting into the austenite, and this is the temperature when you will see that entire perlite and the ferrite, that is alpha, has converted into the gamma. So, above the upper critical temperature we will see whatever alpha and the perlite, ferrite and perlite were there, they have transformed into the austenite. Once we get the homogeneous austenite, this gets it becomes ready for the transformation into the different phases. What if it is heated to further higher temperature, then the size of the austenite grains, here austenite grains are of finer size, and gradually it will keep on increasing. So, here the finer austenite grains will start getting coarsened with the increase in temperature. So, higher is the heating temperature, if it is used, then we will get the coarse austenite grains, while heating just above the upper critical temperature will be leading to the formation of the fine grained austenite. So, for the heat treatment purpose like annealing, normalizing, hardening or quenching, mostly heating above the upper critical temperature, limit is done, so that we get the fully austenitic state. So, this is the use of the iron carbon diagram in the heat treatment, that it helps us to know at what temperature for a given composition of the steel we should heat. Like say if it is having the higher carbon content, say 0.7%, then the temperature at which it will be fully austenitic is this one. So, it will the temperature, upper critical temperature limit, we can see this is the upper critical temperature line, and the upper critical temperature value will keep on decreasing with the increase of the carbon content. For pure iron it is 910, and then with the increase in carbon content of 2.8, it will become minimum value of the 730 degrees centigrade. So, depending upon the carbon content in the steel, this upper critical temperature will be varying, and this shift of this line can be in upward direction or in the lower side, depending upon the alloying elements present in the steel. For example, ferrite stabilizers like chromium, vanadium, tungsten, etc., they tend to move the upper critical temperature line on the higher side, while then austenite stabilizers like manganese, nickel, carbon, etc., they tend to lower down the this upper critical temperature line. So, the size of the gamma loop can be increased for so as per the composition of the steel being heat treated, the suitable upper critical temperature suitable temperature for the heating can be identified from the iron carbon diagram, since the upper critical temperature limit and the lower critical temperature values are the function of the composition. So, this diagram, iron carbon diagram, will help us to see that how the upper critical temperature limit for the heat treatment can be identified for a given composition of the steel. So, now I will summarize this presentation. In this presentation I have talked about the metal strengthening mechanisms and the basic principles which are used for the heat treatment of the steels. I have talked about the iron carbon diagram also, which can be used to find out how to identify the maximum heating temperature for the heat treatment of the steels based on the upper critical temperature limit in light of the composition of the steel. Thank you for your attention.